let's do a brief review. You remember impulse is equal to the force times the time. And we measure impulse in Newton seconds. We discussed when you have an impulse, there has to be some sort of impact or collision. Momentum is the mass of an object times its velocity, and the units for momentum are kilograms meters per second. And the impulse momentum law says the impulse applied to an object is going to be equal to its change in momentum. So Ft is equal to m v final minus v initial. This is how we will mostly write this law. Now remember, momentum of a closed isolated system cannot change. And you remember that when I say closed and isolated, I mean there are no external forces. So there is no friction in these problems. We know, and since the momentum cannot change, that the momentum before a collision has to equal the momentum after. Now our collisions are all going to occur in a straight line. So we'll have two masses, m1, m2, and m1 will come up and, oh, I don't know, impact v2 somehow. And when you see this arrow, I will usually make a big arrow like that. That means collision. That means we've had something happen, and then the two masses, usually we're not going to have a mass change. And we're usually not going to reverse the orders either. But v1 prime, or the velocity of the first one after the collision, will be different. And let's just say we have v2 prime. Now, whenever we do one of these problems, you need to make sure you draw before and after pictures. Use your arrows to show the direction of the motion. So, as I showed you before, I put M1 here, and V1, what I'm saying is this mass is moving to the right. What I'm saying here is this M2 is moving to the left. Velocity is a vector, momentum is a vector, so you have to be very clear about your directions. Usually, just make it go to the right, make it positive unless you're told otherwise. Now, the law of conservation of momentum states that the momentum before equals the momentum after. So we're going to apply this law. There are two kinds of collisions. The first kind that we're going to look at right now is elastic collisions. Now, elastic collisions means they bounce off of each other. So I have two masses, M1 and M2. In this case, they're going towards each other, V1, V2. There is the collision, and they bounce. M1 is still to the left, M2 is to the right. So I've got V1 prime and V2 prime. In elastic collisions, you know, the energy is all conserved. Both potential and kinetic energy do not change, but that is for the system. Any one particular mass could have a change in kinetic energy, but it is the system that has kinetic energy conserved. No heat is formed during this collision. There's no deformation. On a perfectly elastic collision, there'll be no sound. So these are really idealized. Usually, for elastic collisions, we talk about pool. All right, because you have the cue ball, you have the other balls. And this comes about as close as we can get in the real world to modeling elastic collisions. Now, for elastic collisions, your diagrams could look something like this. Now, your diagrams don't need to be in color. They certainly don't need to be fancy shapes. But label M1, this is my first mass. M2, this is my second mass. I have the collision. I have M1 and M2. Now let me show you a way to read this. If you've labeled all of the masses, and if you've labeled the velocities, you can read the conservation of momentum straight off your diagram. Remember, P equals mv. So, m1 times v1 is the momentum of your first ball. m2 times v2 is the momentum of your second ball. This collision tells you what is before and what is after. All right? So, this collision sign is going to come down as an equal sign. On the after side, I have m1 times v1 prime is the momentum of the first ball after collision, and m2 v2 prime is equal to the momentum of the second ball after collision. Now you can see these problems can get to be kind of messy algebraically. So just put your numbers in and make sure you're just as neat as possible. Let's try a problem. Suppose I have a 35-gram bullet moving at 475 meters per second, and it hits a 2.5 kilogram wooden block. The bullet passes through the block, leaving it 275 meters per second. If the block was at rest when it was hit, how fast was it moving? Alright, the first thing you have to do is draw a diagram. Now I've drawn one showing you the bullet and the block. We have an elastic collision, and then the block is moving with some final velocity while the bullet is moving with another final velocity. Now write down your givens and use columns. The first mass is the bullet, and I've converted that to kilograms. 0.335 grams is 0.035 kilograms. The velocity of the first bullet is 475 meters per second, and its final velocity is 275 meters per second. Looking at my second block, it has a mass of 2.5 kilograms. Its initial velocity is 0, and we're looking for its final velocity. Now read the conservation of momentum formula off the top. m1 times v1, m1 times v1, plus m2 times v2 has to equal m1 v1 prime. Now this one did go through. Usually those we don't have things passing through. Plus m2 v2 prime. Now we know this is 0. So wherever you have something that's 0, go ahead and mark it out and make your life easier. And now we want to solve this. All I've done is plug my numbers in. 0.035 times 475. This term right here is 0 equals 0.035 times 275 plus 2.5 times v2 prime. Now, we obviously assume the block didn't get damaged in this. Solving this for v2 prime, I get 16.625 is equal to 9.625 plus 2.5 v prime. So I get a final velocity of 2.8 meters per second.